Hello, good evening students. Today we are going to take up a problem regarding Raoult's law. This problem has been sent to me by one of the students. Raoult's law. Now this law is governing the solutions. Here we have got solution, homogeneous mixture of two or more components in which composition can be varied within certain limits. Now, whatever is present in larger amount, that is known as solvent, and whatever component is present in smaller amount, that is known as solute. So solution is a homogeneous mixture of the two. Here, when you are having a solution, so naturally there comes solubility. The solubility. This is defined as amount of solute in grams required to be dissolved in 100 gram of solvent to get it a saturated solution at a given temperature. Amount of solute in grams required to be dissolved in 100 gram of solvent to get it a saturated solution at a given temperature. Amount of solute in grams required to be dissolved in 100 gram of solvent to get it a saturated solution at given temperature. So for example, you are having salt. So this is added in water. So what will happen? Okay, you will be having this salt will be present in aqueous state. For example, if you are having sodium chloride, so here we are having this. So this indicates the sign of reversibility. The rate of dissolution is equal to rate of precipitation. This is indicating saturated solution. So this is ultimately when equilibrium is there, so rate of forward reaction is equal to rate of backward reaction. If you are having sugar, so sugar is not going to ionize. So sodium chloride is electrolyte, sugar is non-electrolyte. Sugar will be remaining as such in molecular form surrounded by water molecules. So aqueous means here ion, this is ion dipole interaction. The water is a dipole, so naturally here ion dipole interaction. So here lattice is broken and hydration energy has taken over. So this is what we mean by solution. Then we are having solutions. For example, here solute is solid, solvent is liquid. We can have both of them can be liquid also. For example, if you are going to dissolve alcohol in water, it will be liquid in liquid. Here it is solid in liquid, that will be liquid in liquid. If we have got gas in liquid, that is what they call it when we are dissolving gas. For example, in the soft drinks, we are having the gas dissolved in liquid. So there it is governed by Henry's law. In this case, we are having what they call it, the factors which are affecting the solubility. It will be depending upon nature of solvent, nature of solute, then temperature, and pressure comes into being when you are having gas in liquid. We can divide the solutions in two parts. For example, ideal solution and non-ideal solution. Non-ideal solution. Now, before we take up them, first of all, we should know what's meant by Raoult's law. In order to understand this, first of all, we should know vapor pressure. You are having this. Suppose you are having liquid here. It's a closed vessel, and here we have got a manometer tube So naturally in this case this is liquid, here you are having gas. So this liquid is changing into gas and gas is condensing into liquid. So here we have got mercury. At particular point what will happen, the level of mercury in two limbs will be remaining constant. That is indicating the attainment of equilibrium. So this will be equilibrium. Here rate of vaporization is equal to rate of condensation. So as a result of that, here we have got equilibrium state. So the pressure exerted by vapors of liquid at its surface at equilibrium state under given conditions of temperature and pressure will be known as vapor pressure. So this is what we mean by vapor pressure. The pressure exerted by vapors of liquid at its surface at which state? At equilibrium state. So that pressure will be referred as equilibrium, that will be referred as vapor pressure. So what happens when we are adding solute to solvent, for example, suppose sodium chloride is there, so this is non-volatile solute and this is a volatile solvent. What will happen? Suppose it is A, it is B. So here we have got B is added in A. So what will happen? The PA will be the vapor pressure of this will be given by what they call it PA naught. The vapor pressure of solvent is given by what they call it mole fraction of solvent multiplied by vapor pressure of pure A. If both of them are, so naturally here you are having, so this is vapor pressure of solution, here vapor pressure of pure solvent. This is the mole fraction of this. Now it means the vapor pressure is how it is derived. For example, vapor pressure is proportional to XA. So naturally PA is equal to K into XA. Now when XA is equal to 1, so then PA will be equal to PA naught and equal to K, and this formula will be coming. So vapor pressure in solution is proportional to, it is mole fraction. Here it is sign of proportionality. Now if XA is equal to 1, it means only one component is present. So this XA is equal to 1, so K will be equal to PA. Now only A is present, so this will be referred as PA naught. So K the value put kar do, naturally you will be getting this formula. So if both of them are volatile, so then partial pressure of A will be given by this, partial pressure of B will be given by this. If both of them are volatile, so naturally this is the partial pressure of A in solution and partial pressure of B in its solution. So this will be given by this formula. So this is as per Raoult's law. So what is ideal and non-ideal solution? Ideal solution means when solution is obeying Raoult's law. Right? So this second delta H mixing is equal to 0. Delta V mixing is also 0. So here, for example, you are having benzene and toluene. Benzene and toluene upon mixing, what will happen? The van der Waals forces of attraction are there in case of benzene, same type of forces are there in toluene. So when you are mixing them, no change is taking place. So naturally neither heat is evolving nor it is given out. So delta H mixing will be 0. So here when you are mixing, so naturally bonds are neither breaking nor being formed. So naturally final volume delta V mixing means the final volume after mixing minus initial volume before mixing. That will be same, so resultant will be, you can say, 0. So this is what we mean by ideal solution. So ideal solution will be having satisfying these conditions. For example, this will be the Raoult's law obeying, then delta H mixing is 0, delta V mixing is 0, because no new forces are created or old forces are destroyed. So naturally no heat is produced or absorbed. No change in volume. 10 cc of benzene mixed with 10 cc of toluene. Before mixing volume is 20. After mixing again it is 20. So final minus initial, no change. So this is delta V mixing is 0. So here how we can show it by graph? It is like this. So here we have got, say, so this is XA is equal to 1, XB is equal to 0, XB is equal to 1, XA is equal to 0. Here vapor pressure, and this is the total pressure, PA plus PB. So here it is PA is equal to PA naught into XA. Here it is PB is equal to PB naught into XB. So this is for this. So this is the ideal solution. Here we have shown it should be something different, otherwise it is same level. So here we should show it like this. So that's somewhat. So this is slightly different. So as a result of that, what will happen? We will be having so this is the situation. Here vapor pressure of this. So this is the situation for what they call it ideal solution. Then what is non-ideal solution? Here Raoult's law is being obeyed. Here Raoult's law is not obeyed. For example, you are having two types of non-ideal solution. One is showing positive deviation, second is showing negative deviation. Positive deviation and negative deviation. Positive deviation means that PA will be greater than PA naught into XA, PB will be greater than this, delta H mixing will be positive, delta V mixing will be positive, right? So here you are having example of alcohol and cyclohexane. Alcohol and cyclohexane, when you are mixing them, what will happen? It will be resulting into bond breakage. Which bond is breaking in alcohol? Hydrogen bond is breaking. So naturally cyclohexane is intervening, resulting into breakage of hydrogen bonds of alcohol. When bonds are breaking, delta H will become positive. Then if you are mixing 10 cc of each, before mixing volume is 20 cc, after mixing bonds have broken, so expansion has taken place, so naturally final volume is greater than initial volume, delta V mixing will be also positive. Now here when delta H mixing is positive, positive deviation. Delta H mixing is positive. So what will happen? The solubility will be increasing with rise in temperature, because during formation of solution heat is absorbed. you supply the heat, solubility will be increasing. So heat will be absorbed during this solution. So delta H mixing means the solubility will be increasing with rise in temperature. This is as per law Leach-Chatelier's principle as well as thermodynamics gives Helmholtz equation. What was that equation? Delta G is equal to delta H minus T delta S. Here delta H is positive, T is increasing, so delta S is positive. So naturally, in order to have this as a dominating factor, because this is opposing factor, so here temperature has to be kept high. So this is as per thermodynamics, and thermodynamics the application is there in case of chemical equilibrium, and solution is also application of thermodynamics. So this is the what they call it solution, which is you can say showing positive deviation. How it is looking? In this case, the graph will be like this. So here you will be having this will be greater than this will be greater than this, and P will be equal to this. So here solution of positive deviation. Then the second type is the solution showing negative deviation. Non-ideal solution showing negative deviation. Negative deviation. Negative, for example, chloroform and acetone. Chloroform and acetone, when you are mixing them, what will happen? Chloroform will be making so hydrogen bond is formed. Hydrogen and oxygen are making bond. The bond formation is taking place. So here, first of all, PA, Raoult's law is not obeyed. So PA will be something less than this. PB will be less than delta H mixing is negative, delta V mixing is negative, because bond formation is taking place, shrinkage is there, so final volume will be smaller than initial volume. Here bonds are formed, so heat is produced. So naturally solubility will be decreasing with rise in temperature as per Leach-Chatelier's principle as well as Gibbs Helmholtz equation. So in this case, the graph should be like this. It will be like this. So here the graph will be like this. So graphs are showing different types. Here this orderly graph is meant for ideal solution. This reddish is one for positive deviation, and this dark black is indicating the negative deviation. So when you are having non-ideal solution, then you are having azeotropic mixtures. Azeotropic mixtures means the mixtures, for example, A and B are solution of A and B are forming a non-ideal solution. So here how to separate them? By using fractional distillation. At a certain stage, what will happen? Initially, what will happen? The more volatile component will be vaporizing first, and then it will be passing into liquid state earlier. But when you are having some non-ideal solution, so a state will come when both components start boiling at same temperature, right? For example, negative deviation is showing you what they call it maximum boiling. This is maximum boiling azeotrope, and positive deviation will be forming azeotrope with minimum boiling. Because what is boiling point? Boiling point means the temperature at which vapor pressure becomes equals to atmospheric pressure. So as a result of that, the azeotropic mixtures are there in case of non-ideal solution. Now we have already seen, for example, here you are having PA naught minus PA upon PA naught is giving you is equal to XB. Relative lowering of vapor pressure is equal to mole fraction of solute. So this is relative lowering of vapor pressure is a colligative property. Relative lowering of vapor pressure is a colligative property. Now mole fraction is equal to WB upon MB. Mole fraction is equal to this. Here it is MB upon, what is XB? XB is equal to NB upon NB plus NA. So this is NB, here WB upon MB plus WA upon MA. W is weight of particular substance, M is molecular mass. So as a result of that, first of all, colligative property is directly proportional to concentration of solute. What is colligative property? Which is depending upon quantity of solute. Now here, what that quantity is taken in mole fraction. So here if you take, because out of W, this denominator, this is very large, this is small, so we are neglecting this. So as a result of that, WB upon MB is equal to WA upon MA. So as a result of that, this will be PA naught minus PA upon PA naught is equal to WB upon MB into MA upon WA. So therefore, here the molecular mass of solute is inversely proportional to colligative property. So colligative property is directly proportional to amount of solute. It is inversely proportional to molecular weight of solute. So here we have got Vanthoff factor. It is I. It is given by observed colligative property over normal colligative property. Observed means whatever we have determined experimentally. Normal means whatever it should be theoretically. So for ideal solution, I is equal to 0. And for non-ideal solution, I is not equal to, this is 1. Here it is 1, it is not equal to 1. In ideal solution, I Vanthoff factor is equal to 1. In non-ideal solution, it is not equal to 1. For example, solution showing positive deviation. Positive deviation. Positive deviation means that here we have got, in this case, you are having non-ideal solution. It can be, for example, solute can be getting dissociated. Solute is getting dissociated in solution. Here I is greater than 1. Solute getting associated in solution. Here I is less than 1. So this is the situation for non-ideal solution. Non-ideal solution वास्ते की है कि here we are having I will not be equal to 1. For example, dissociation means कि when you are adding solute in solvent, dissociation will be leading to larger number of particles. Larger number of particles means colligative property will be higher than whatever we are expecting. So observed will be smaller than what they call it. Observed will be smaller than, you can say, observed will be greater than normal one. In the case of association, we have added say 100 particles and they have associated, say dimerization has taken place. Now in solution they are 50. So as a result of that, I will be less than that. So as a result of that, what we are having, non-ideal solution, their Vanthoff factor is not equal to 1. For example, let us take the case of sodium chloride plus this. Here we have got, say, we have added one molecule of this. Initially 1, 0, 0. After some time, alpha has dissociated. Here it is alpha, here it is alpha. The number of particles in solutions are alpha and alpha. So as a result of that, we were expecting the colligative property as per one particle. While actual, the normal colligative property was proportional to one particle. Observed colligative property will be, it will be proportional to 1 minus alpha plus alpha plus alpha. It is 1 plus alpha. So therefore, I will be equal to 1 plus alpha over 1. So as a result of that, for dissociation, I will be greater than 1. So what is I? I is Vanthoff factor. What is alpha? Alpha is known as degree of dissociation. Degree of dissociation is always out of 1. So 1 out of 1 means 100% dissociation. 0.2 out of 1 means 20% dissociation. So this is degree of dissociation is there in case of ionic equilibrium also. So naturally here if you have got concentration 1, it is 1 minus alpha. If it is C, it will be C into 1 minus alpha. C alpha, C alpha. So naturally it will be C into 1 minus alpha, C alpha and C. C is common and C will be here. So naturally C and C cancel, only Baki will be again left with 1 plus alpha. So this is the case with, so here what will happen, the molecular mass of sodium chloride is, it is 2358.5. But actual, this is the normal molecular mass of, normal formula mass of sodium chloride. But the molecular mass determined with the help of colligative property will be turning out to be 29 only. Why it is so? Because of dissociation. Because the observed colligative property is something, what they call it, greater than normal colligative property. So as a result of that, here we have got I can be also put in terms of this. So I can be normal molar mass of solute over observed molar mass of solute. Normal means, for example, you are having sodium chloride, the normal molecular mass is 58.5. Observed is something determined, that is 29. 58 over 29, approximately 2. So this is the situation for dissociation when the solute is undergoing dissociation. Similarly, we can also have the case of association. For example, benzene is getting associated. So let us take the case of that. n molecules of A are getting associated to form a polymer. So you are having this initial concentration 1, 0. Concentration at a particular state. It is 1 minus alpha. Here it's alpha over n. So what is the, so here observed colligator property will be over normal colligator property. It is 1 minus alpha plus alpha over n over 1. So naturally this I will be something less than 1. What is alpha? Alpha is known as degree of association. Earlier it was known as degree of dissociation. Now it is known as degree of association. And what is n? N is known as extent of polymerization. For example, if you are having this, say it is 2. So here dimer is formed. So what is n? N is extent of polymerization. So n is extent of polymerization. Alpha is degree of association. And what is I? I is known as Vanthoff factor. So this is the case of association. This is the case of dissociation. So therefore, whenever we are to solve numerical, we should consider the Vanthoff factor. For example, delta TB is equal to, this is Kb into what they call it. This is what they molality. This is molality. I into this delta TF, I into Kf into M. Then you have got osmotic pressure. It is I into CRT. So I has to be introduced every time. If I is equal to 1, then it is normal solution. It is something what they call it ideal solution. And molecular observed molecular mass and normal molecular mass will be same. If it is something association or dissociation is taking place, then we'll have to take into consideration that. So that will be giving you the correct results. So I factor has to be introduced, has to be kept in mind. So that will be giving you the correct results. So this was something from what they call it Raoult Law. This problem was sent by one of the students. So you are always welcome to bring your problem. So try to solve the problem. For example, I told you why the solubility increases or decreases with rise in temperature, depending upon Gibbs-Helmholtz equation or Lee-Chatelain's principle. Gibbs-Helmholtz equation comes in thermodynamics, chemical equilibrium, solution, electrochemistry, all are the application of thermodynamics. So one should know the sequence, one should know the context in which we are studying. So that's all for today. I hope you will be must have come to know quite a number of things. So try to have better standards. So keep on solving problems. Whatever problem you come across, so that should be brought to me or your class teacher or your friends, as we have been always suggesting. So, but keep on having self-study to the maximum possible extent, 7-8 hours daily. So that will be the secret of your success. That's all. Thank you.